Hello, abstract algebra students. We will now begin the proof that the power set is closed under symmetric difference. This proof is another element chasing proof, but it is not as long as well defined. So I'm just going to type it into PowerPoint. And if this screencast starts to feel long, well, then I'll split it up into two screencasts. So our claim is the power set P of M is closed under symmetric difference. So the first thing that we do is we figure out what we want to show here. So elements of the power set are sets. So we'll use A and B as capital letters here. So we want to show for every AB, if both A is a member of the P of M, and B is a member of P of M, then asymmetric difference B is a member of P of M. Okay. This is a quantified if-then statement, so we should have seen enough of these now that we know what the first two sentences should be. Let AB be given to capture the for all quantifier. Assume that both A is a member of P of M, so A is in the power set P of M, and B is a member of P of M. Now, once we make our assumptions, we need to unwrap our assumptions. So, since we know that both A is a member of P of M and B is a member of P of M, let's think about what that means. To be in the power set, you have to be a subset of M, because the power set of M is the set of all subsets of M. So since we know both A is a member of P of M and B is a member of P of M, by definition of power set, it follows that both A is a subset of M and B is a subset of M. Now, if I don't see where I want to go next, let's reason backwards from where I want to end up. So if I put some virtual scrap paper here, I want to end up showing that asymmetric difference B is a member of the power set of M. This means that I want to show that asymmetric difference B is a subset of M, because remember, once again, you are an element of the power set when you are a subset. This power set is the set of all subsets. So I want to prove that asymmetric difference B is a subset of M. But by definition of subset, that means I need to prove for every element X, if X is a member of asymmetric difference B, then X is a member of M. Okay, so what this is telling me is that I need to element chase. So consider the following claim. I'm going to go into an element chasing claim. So my element chasing claim is for every X, if X is a member of A intersection B, then X is a if X is a member of asymmetric difference B, then X is a member of M. I'll come back and do the element chasing proof shortly, but first I just want to wrap up where this goes. Once we are done with this, we can say, having proven that for all X, if X is a member of A intersection asymmetric difference B, then X is a member of M. By the definition of subset, it follows that asymmetric difference B is a subset of M. Therefore, since we know that asymmetric difference B is a subset of M, by definition of power set, we may conclude that asymmetric difference B is a member of the power set P of M. Therefore, since we know asymmetric difference B is a subset of M, by definition of power set, we may conclude asymmetric difference B is in P of M. And that ends the proof. Now, we of course still have to do that element chasing, and I will fill that in on the next video. However, once we have finished the element chasing, this is what our proof will end up looking. Notice the key here was knowing what the definition of power set meant to be able to go from A is in P of M and B is in P of M to A is a subset of M and B is a subset of M. And also knowing that I need to work backwards from asymmetric difference B is in P of M to asymmetric difference B is a subset of M to this element chasing claim. For all X, if X is a member of asymmetric difference B, then X is a member of M. We will fill in the element chasing claim on the next video. Stay tuned.